Hello everyone from Math 2000, Linear Algebra. Professor Winson here again with a video on your Zybooks section 8.3 titled Similarity and Diagonalization. So let's just get into it. Alright, so some matrices are similar to a diagonal matrix. Now, what that means we'll get into in a second. Alright. A square matrix with 0 entries everywhere except along the diagonal, right? That's what a diagonal matrix is. But what does it mean for two matrices to be similar to one another? That's what we're going to get into down here. Finding the corresponding diagonal matrix is useful because the square matrix and the diagonal matrix have the same determinant, rank, nullity, and eigenvalues, right? So it's going to be really nice to know when to, when two matrices are similar, they'll have the same determinant, rank, nullity, and eigenvalues. The eigenvalues and eigenvectors of a square matrix can be used to determine whether a matrix is similar to a diagonal matrix, and to find the corresponding diagonal matrix when possible. Alright, so I really don't think this is a great summary, to be honest. It introduces what's going to happen in the section, but I think it introduces some words too early. You don't know what the word similar means yet in matrix, but we'll get to that down here right now. Okay. So what does it mean for two matrices to be similar to one another? So two n by n matrices, say A and B, are similar if an invertible n by n matrix called M exists such that B is equal to M inverse times A times M. Or if you multiply by M on the left of both sides, this relation can also be expressed as M times B equals A times M. So in other words, a matrix B and A are similar if there's another matrix, an invertible matrix called M, such that when you multiply A on the right by M, you get the same as if you multiply the other matrix on the left by M. Right, so it's kind of like, it's almost like a commutative property, but not, it's not M times B equals B times M. It's, multiplying one matrix on the left by M gives me the same result as multiplying this other matrix on the right by M. And if that's the case, then these matrices A and B are called similar. Alright, so look at these examples here. Alright, I'll just read this first one off. They say here, consider matrices A is this 3 by 3 matrix here, and another matrix M, and this matrix M is invertible, and here they give us the inverse of M. Alright, so these two matrices are inverses. Now if you were to take M inverse times A times M, you'll get another matrix that's said to be similar to A. So they've done that here. They've taken M inverse times A times M and gotten this new matrix, which we're calling B. This new matrix is said to be similar to the matrix A. So matrix A and matrix B are similar. Meaning that you could multiply A on the right by M and get the same result as if you were to multiply B on the left by M. All right, which I will show you here as well. Okay, so up on the screen has popped my calculator. And in this I have created a matrix A. That's a 3 by 3, which is this matrix A here in the activity with the 140, negative 101, and 115 rows. The matrix B in my calculator is this matrix B in the activity with the 13, 34, negative 13, negative 12, 27, 11, negative 22, negative 47, and 20 rows. And the matrix I called C in my calculator is this matrix M with the negative 1, negative 5, 2, 1, 3, negative 1, negative 2, negative 5, 2. And again, C, this matrix C or M is invertible. Right? It has an inverse as they've shown us. So like I said, this matrix A and matrix B are again considered similar matrices because you can find an invertible matrix such that if you multiply one of them on the left and the other one on the right by that invertible matrix, you get the same result. Right? So let me get out of here. I'm going to make calculation screen. I'm going to take my matrix C, which was the matrix M, and multiply it by matrix A. All right, so you see you get this 6, negative 2, 5, negative 3, 3, negative 2, 5, negative 6, 5 entry matrix. So that's matrix A multiplied on the left by, oops, I should do it on the right. Sorry, I should do it on the right because look, they got matrix B here by taking M inverse times A times M. All right, so if I multiply on the left by M, I'll have MB equals AM. So I should have done it the other way around. Sorry. So if I take matrix A and multiply it by C on the right, I get this matrix, 3, 7, negative 2, negative 1, 0, 0, negative 10, negative 27, 11. That should be the same, right? A times M on the right should be the same as M times B. So I take M times B or C times B on my calculator. So let's take the matrix C and then times it by matrix B. And you see I get the same result. No, I don't. Why? Maybe I mistyped something. Okay, so I've discovered the error. And I guess I'll point this out to you because I'm gonna leave some feedback here. When you multiply these three matrices, M inverse times A times M, and I did this on my calculator, I made sure I entered everything correctly. It should be 13, 34, negative 13, negative 12, negative 27, 11, and then negative 22, negative 47, 20. So they're missing a minus sign on the 27 here. All right, so I'm going to go back to my matrix B. So I apologize for this. This wasn't my mistake. It's just I should have caught this error earlier. So I go back to my matrix B here, and I'm going to change that 27 in the second row, second column to a negative 27. All right, and now this stuff should work. So now M times B should be equal to A times M, or in my calculator, C times B should be equal to A times C. All right, so let's check that. So matrix, so C times B, I'll do C times B first, is this matrix with the 3, 7, negative 2, negative 1, 0, 0, negative 10, negative 27, 11. That should be equal, now that I've fixed the error on their page here, again this is minus 27, not positive 27 in matrix B here. Now that I fixed their error, this should be equal to A times M or A times C on my calculator. All right, and indeed they are. Okay, you see the 3, 7, negative 2, negative 1, 0, 0, negative 10, negative 27, 11. It's exactly the same matrix I got when I did C times B. So, this matrix A and this matrix B, but with a negative 27, are similar matrices. Okay, so got that little snafu out of the way. Now they're asking us in the following activity to verify, that, well, find a matrix that's similar to a given matrix. All right, so I'll write this one out on paper. So if they're saying find the matrix similar to A using, invertible matrix M given this equation. So you really just pop it into this equation right here. All right. Let me show you. Okay, so we have this matrix A, 2 by 2, and then this invertible, this other matrix, this M, should be an invertible matrix, and this is, right, the determinant is negative 1, that'd be 0 minus 1. So the inverse is pretty easy to find, right? Remember, for 2 by 2s, it's very simple. I have the reciprocal of the determinant, which, the reciprocal of negative 1 is just negative 1. And then I switch the diagonal, the main diagonal entries and take the opposites of the other two entries and multiply each of these by negative 1. We have 0, 1, 1, negative 1. All right. Okay. Then you can verify that these are inverses by multiplying them, seeing that you get the identity matrix. Now, I'm going to use this to find a matrix that's similar to matrix A. A matrix similar to A. Well, again, they're calling this B, right? And one way to do it is to take, this inverse, M inverse, multiply it by A, and then multiply it by M. And let's see what we get. M inverse, 0, 1, 1, negative 1, times A, negative 3, 1, 5, 2, times M, 1, 1, 1, 0. Now, remember, matrix multiplication is associative. I'll just go right to left here. All right, so let's multiply these two. So it's going to be 0, 1, 1, negative 1. And the 2 by 2 times the 2 by 2 is another 2 by 2. And, you know how to do matrix multiplication by now. That's negative 3 plus 1, so negative 2 there. Negative 3 plus 0. And then 5 plus 2. 5 plus 0. Right, and then multiplying these two gives me another 2 by 2. We've got 0 plus 7. 0 plus 5. Then negative 2 plus negative 7, and negative 3 plus negative 5, and there you go. So here's this matrix, B, with entries 7, 5, and negative 9 and negative 8. This matrix is said to be similar to A. Right, and the reason being is that you can find an invertible matrix, called M here. If I were to take this equation and multiply on the left side by M, we'd have M times B would be equal to A times M. And that's why they're similar, because when I multiply by this fixed matrix M, and I multiply one matrix on the left, the other matrix on the right, I get the same thing. So these two matrices must be, similar in some way. Pardon me. And we could test this, make sure that this is actually happening. All right, so M, let's take M times B here. And that'll give me what? 7 plus negative 9 is negative 2, and then 5 plus negative 8 is negative 3. And then 7 plus 0, 5 plus 0. So that's M times B. And now let's take A times M and see if I get the same thing. Negative 3, 1, here's A times M. And hopefully I get the same thing, right? Well, I did this earlier actually. Right, I did that up here. That was this, negative 2, negative 3, 7, 5. And you see how they are indeed the same result. So multiplying by, B on the left by M gives me the same result as multiplying A on the right by the same matrix, M. So A and B must have some sort of similarity. Okay. So, yeah, the matrix B, though, that they were looking for is this one, right? What's a similar matrix to matrix A? This 7, 5, negative 9, negative 8. And you're asked to do the same here. Okay, now you could use a calculator, of course, now these have lots of zeros and blocks of 2 by 2s, so it might not be so hard to figure out what M inverse is, but if you want, I would suggest just enter this as a 4 by 4 matrix in your calculator. This is another 4 by 4 matrix, and then take M inverse times A times M, and you'll get the matrix B that should be similar. Right, now it's definitely not this second option. Right? Matrices that are similar are going to have the same size. So A was a 4 by 4. Any similar matrix to it should also be a 4 by 4. Right. Now, this theorem, these statements were mentioned in the summary at the beginning of the section. So if A and B are similar matrices, then the following statements are true. A and B will have the same determinant. All right, so going back and looking at the last example I just did, right, let's take a look again. All right, here was here was A. Now the determinant of A is what? Negative 6 minus 5, that's negative 11. And we said it was similar to this matrix here, right, with the M inverse times A times M, similar to this matrix B. And what's the determinant of that matrix? Well, according to our theorem there, it should also be negative 11 if they truly are similar. Let's see, that'd be negative 56 minus negative 45 or plus 45. That is indeed negative 11. So the determinants of similar matrices are equal. Right. A is invertible if and only if B is invertible. All this comes from the fact that they have the same determinant, right? If they're both determinant 0, then they're both not invertible. And if they both have determinants that aren't 0, like in my example with the negative 11, then they're both invertible. All right, so this is just, statement 2 is just saying that two similar matrices are either both invertible or they're both not invertible. Number 3. Two similar matrices will have the same rank. And if they have the same rank, then they'll also have the same nullity. All right. So again, back here, the rank of matrix A. Now you can find the rank in a couple ways, but remember, one easy way was just to look. Now there's only 2 columns here, or you could think of the rows as well. And if you look at these column vectors, are these column vectors scalar multiples of one another? No, they're not. So both column vectors are independent. And remember, the rank of a matrix was the number of independent column vectors. Or if you were to put it in reduced row echelon form, right, or even just echelon form, it would be the number of pivot columns. Well, the rank of A is 2. Same thing for B. Right, these two, 7, -9, that column vector, and 5, -8, those are not scalar multiples of each other. So we have 2 independent column vectors. So the rank of B is also 2. And this is going to happen for any pair of similar matrices. They will have the same rank. And again, if they have the same rank, they'll also have the same nullity. Both of these matrices would have a nullity of 0. And then the final one here, which maybe isn't as obvious, 2 similar matrices will have the same spectrum. Now remember, the spectrum of a matrix was the the set of eigenvalues. So if I found the eigenvalues of A, right, which I'll do real quick, just to refresh your memory. So remember how to find the eigenvalues of a matrix, right? You set up that characteristic equation. When is the determinant of A minus lambda I, when is that equal to 0? So that'd be the determinant of this matrix, -3 minus lambda, 2 minus lambda down the diagonal, 1 then 5 like that. And when I multiply these two, I get lambda squared, then plus 3 lambda, minus 2 lambda would be plus lambda, and then minus 6, right? Minus 6, and then we have minus 5, so it'll be minus 11. And then I solve this, quadratic equation. Right? And you could do it by completing the square. I'll just use the quadratic formula here real quick. It'd be -1 plus or minus. There'd be 2 of these. Square root of b squared minus 4ac, right? Be plus 44. Then all this divided by 2, and so we're getting 2 solutions here, 2 eigenvalues. Now the square root of 45 can be written as 3 times the square root of 5, right? Square root of 9 times square root of 5. There we go. -1 plus 3 root 5 all over 2, -1 minus 3 root 5 all over 2. And this is the spectrum of matrix A, the set of all the eigenvalues. Well, without even trying, those are the same eigenvalues as B. Right? And if I'll just set up the characteristic equation and show you. All right, I'm not going to actually finish solving, because what you're going to see is the characteristic equation will look the same. So if I do the determinant of b minus lambda I, when is that equal to 0? So again, that's this determinant here. Do 7 minus lambda, -8 minus lambda, 5 and -9. Then I do this product here. I'll have lambda squared. Then you have minus 7 lambda plus 8 lambda would be plus lambda. Then minus 56 plus 45 would be, hey, look at this, minus 11 equals 0. Same characteristic equation as earlier. So two similar matrices are going to have the same characteristic equation, therefore the same eigenvalues. Right, and this is just one example, but that will always happen. Okay, and they give a proof and whatnot. You can read that if you want. All right. Then here's another part, showing that similar matrices, have the same spectrum. Basically showing that the determinant of b minus lambda I would be the same as the determinant of a minus lambda I. They have you write reasons for all the steps. So like the first step they're starting out with is they're saying, hey, let A and B be similar matrices. So this is by definition of similarity, right? If A and B are similar, there should be some invertible matrix M such that this is true, that B equals M inverse times A times M. So the definition of similar matrices would be the first line of reasoning, right? For that first line there. Let me actually get this in. There we go. All right, and then notice what they did here was they subtracted lambda I from both sides. That's just the subtraction property of equality, right? When you have an equation, you can subtract the same thing from both sides and you'll still have an equality. So I'll make that the second line of reasoning. And look at the third line. What happened here? Well, see how they changed these i's? Well, they changed this I anyway to M inverse times M. And they changed B here to M inverse times A times M from the first line. So really what they used there was definition of inverse matrices. Actually, they made two substitutions. I don't like this. They should have just made one at a time. But they replaced the B on the left with M inverse times A times M, right, from the first line. And they replaced the I on the right with M inverse times M. And you can say that I is equal to M inverse times M because that's how inverse matrices are defined. You multiply two inverses, you get the identity matrix. Then the next line, they did it again. They changed this I on the left to M inverse times M. So they do another definition of inverse matrices. But they did something else too. Okay, so they changed that. And then over here, see, they factored out M inverse on the left and M on the right. So they did the distributive properties, right? Use the left distributive property with M inverse and the right distributive property with M. Okay. So then taking the determinant of both sides, you have the determinant of B minus lambda I is equal to this determinant over here, which you can break up. Remember, the determinant of a product is the product of the determinants. That's this multiplication property of determinants. All right, and then you obviously got the last one. Yeah. All right, well, for some reason it didn't pop in there. And then finally, the determinant of M inverse times the determinant of M should be 1, right? The determinants of inverse matrices will be the last reasoning why those are gotten rid of. So you can see after all said and done here, the determinant of B minus lambda I is exactly the same as the determinant of A minus lambda I when A and B are similar. And you saw an example of this, right? You saw that example here. Right? The determinant of A minus lambda I and B minus lambda I for these two similar matrices, both of those were lambda squared plus lambda minus 11. All right, that's just one example. All right, so now comes the heart of the section. All right, we talked about what it means for two matrices to be similar, and how do I find a matrix that's similar to another matrix, right? You just need to find, you can really use any invertible matrix for M. as long as they're the same size as the matrices A and B. All right, so diagonalization. So the big question here is, if you're given a matrix, now they're doing powers of matrices here. I'll go to a piece of paper and write out a very big question. And the question that we're going to be answering in this, second half of this section. So, given a matrix, a square matrix A, is there an invertible matrix, same size, right? Is there an invertible matrix say P or M? I'm using P because they're for some reason changing it to P later in the text. Is there an invertible matrix P such that P inverse times A times P equals D, where this D here is a diagonal matrix? In other words, or another way of saying that, asking that question, is matrix A similar to a diagonal matrix? And if it is, right, if there is this matrix P that this happens, then we say that matrix A is diagonalizable. Right? And that's if your matrix is similar to a diagonal matrix. Right? So they start off here with an application. Many applications of linear transformations involve using compositions of the same transformation with itself, which implies raising a matrix to some power, right? You just keep multiplying by the same transformation matrix over and over again. However, calculating large powers of matrices directly can become cumbersome, right, or tedious. For example, say A was, this 3 by 3 matrix here, and they say, well, what's A to the 5th power? Well, that means multiply that matrix by itself 5 times. And in doing so, they end up with, this 3 by 3 at the end here. Here's A to the 5th. A to the 5th. Well, what we're going to see is that if we can find a diagonal matrix that A is similar to, it'll be very easy to take higher and higher powers of A instead of having to do it long. Now the 5th power isn't that high, but we'll see that you could even use the fact that A is similar to a diagonal matrix. You're going to be able to use that fact to maybe even raise, you could raise A to the 100th power, the 1000th power, and do it relatively easily. I'll show you here. So see, for this A to the 5th example, they're saying, however, A to the 5th can be calculated indirectly by using the definition of similarity with P and D. Right, so P, notice that this is that invertible matrix. This is like the M earlier, but now it's P for some reason. And see, D here is a diagonal matrix with just entries down the main diagonal and zeros everywhere else. So what they're showing you here is that basically A and D are similar. And if they are similar, if your matrix is similar to a diagonal matrix, and you solve for A, earlier I had D equals P inverse times A times P. This is just multiplying by p on the left, multiplying by p inverse on the right, switching sides here, solving for a. So if you have a equals p times d times p inverse, where p is some invertible matrix and d is diagonal, see if I raise this to the fifth, what happens is a lot of those p's and p inverses will become the identity matrix and kind of cancel out. And what you end up with is, a to the fifth is p times d to the fifth times p inverse. And a diagonal matrix raised to higher and higher powers is very simple to take. D to the fifth would just simply be the same matrix, but down the main diagonal, you raise the main diagonal entries to that power. 5 to the fifth, negative 1 to the fifth, which would be negative 1, and then negative 1 to the fifth again, which they're doing here. And so you see, raising a to the fifth power, instead of multiplying 5 matrices, we would only need to multiply 3. That invertible matrix P by the diagonal to the fifth power, which again would be easy to take, and then by P inverse. So it cuts down the number of calculations significantly, especially if you had higher powers than even 5, right? If I asked for what's a to the 100th power, you'd have your matrix P, then you'd just raise all the diagonal entries in D to the 100th power, and then multiply by P inverse. And again, even raising to the 100th power would only require multiplying 3 matrices instead of 100. All right, and hopefully, reading all this out, this one example here is not helping us. So, how'd they find this P? How'd they find this D? Where'd these come from? We're going to get into that. All right, we're going to see how do I take a matrix and determine if it's similar to a diagonal matrix, and if so, what is that diagonal matrix, and what is that invertible matrix, P. So we'll get to that here in a second. All right. So another highlight here. So diagonalization is the process of finding this invertible matrix P and this diagonal matrix D such that A equals P times D times P inverse. So finding a matrix P that diagonalizes A is closely related to finding the eigenvalues and eigenvectors of A. The theorem below provides a criterion for the diagonalizability of matrices. All right. So here's the key. Right. An n by n matrix A is diagonalizable if and only if. So this is necessary and sufficient conditions. A has n linearly independent eigenvectors, say v1 through vn. If the matrix does not have a set of n linearly independent eigenvectors, then that matrix is not diagonalizable, meaning it's not going to be similar to any diagonal matrix. So that leads us to the procedure. All right. In fact, the matrix P, how I asked, how I said, how'd they know what this matrix P was? The matrix P, each column is an eigenvector, right, of A. Each column in this matrix P here is an independent. All 3 of these are independent eigenvectors of A. And then the diagonal matrix, the entries down the main diagonal are the eigenvalues of A, and they come in the same order of their corresponding eigenvectors in matrix P. Meaning that 5 was an eigenvalue corresponding to the vector 1, 1, 1 for matrix A. -1 is an eigenvalue corresponding to the eigenvector -1, 1, 0. And this -1 here is an eigenvalue corresponding to the eigenvector -1, 0, 1. So you're going to see the eigenvalues show up on the diagonal in the same order as their corresponding eigenvectors, in the columns of this P. All right. So the first questions here, these first examples, are just simply determine whether the matrix is diagonalizable. So does the matrix have, n independent eigenvectors that you can use? So I'll write out this first one. So first, I'll go through the steps here. Find the eigenvalues, right? Find the spectrum of A. So I set up the characteristic equation. Right? When is the determinant of A minus lambda I equal to 0? So that's the determinant here. You got 6 minus lambda, 3 minus lambda down the diagonal, and then every other entry is the same. Alright, then when I multiply these two, I'm getting lambda squared, minus 3 lambda, minus 6 lambda, be minus 9 lambda, and then plus 18, but then you got minus negative 2, right, so plus 20. And this factors nicely to lambda minus 5 times lambda minus 4. Alright, so the spectrum of A is 4 and 5. Right? Those are the eigenvalues. Now right away, I can tell you that this matrix is what they call diagonalizable. Because if you recall from section 8.1, right, section 8.1, when you were introduced to finding eigenvalues and corresponding eigenvectors, the eigenvectors for different eigenvalues, right, distinct, 4 and 5 are distinct eigenvalues. Remember, the eigenvectors for distinct eigenvalues are independent. So see, I have two distinct eigenvalues. So that means that I will have two, we can find two independent eigenvectors. And if that's the case, this is a 2 by 2 matrix. Right? And that theorem I stated a second ago was that an n by n matrix is diagonalizable, right, similar to a diagonal matrix, if and only if it has n independent eigenvectors. Well, again, this is a 2 by 2, so it's only going to be diagonalizable if you can find two independent eigenvectors, which we can. So without even finding them, I can tell you that A is what they call diagonalizable. All right, and let me actually just go into the process of doing this. All right. Now again, if A is diagonalizable, what does that mean? This means that we can find a matrix P such that P inverse times A times P is equal to a diagonal matrix. Or the way they've been writing it is, A is equal to P times D times P inverse, right? All they're doing is putting P on the, multiplying by P on the left, multiplying by P inverse on the right. These are the same equation, right? But I would like to find this diagonal matrix. Now again, the matrix P, how do we find this? Well, you find these independent eigenvectors. So now let's actually get into it, right? I've already answered their question. But now I'm going to continue the process, and I'll do more examples of this later in the video as well. So now let's find eigenvectors, corresponding to these eigenvalues. All right, really I want to find eigenbases. I want to find the eigenspaces and then the basis for each eigenspace. All right, so for lambda equals 4. All right, for lambda equals 4. We're solving, remember this equation here, right? A minus 4i, times what vectors gives me the 0 vector. All right, now a minus 4i. That's just taking a and subtracting 4 down the diagonal. So that's 2 and negative 1. Got negative 1 here, 2 there. Then times some vector x equals the 0 vector with 2 components. And putting this into reduced echelon form is pretty simple. There's only 2 rows. These are the same thing, so I can get rid of the second row, no problem. And then the first row I'd multiply by a half, to get that lead 1. Right, so there's reduced echelon form. And then my first component, x1 will be a basic variable. x2 is free. And since there's that fraction there, I'm going to have x2 be, just get rid of the 2. I'm going to have x2 be represented by the expression 2 times t, where t is any real number. And then if that's the case, if I let x2 be 2 times t, then this first equation is telling me that x1 must be t. Right, because negative half times 2t would be negative t. This is x1 minus t equals 0, add t. So, the eigenspace of this matrix, corresponding to lambda equals 4, is the span of the vector, 1, 2. Right, that's t times 1, that's t times 2. It's only got a dimension of 1. But this is what I'll use. All right, this vector 1, 2. I'm going to use this vector, and really you could use any multiple of this vector, or as long as you pick a vector from here. But I'll just use 1, 2. This will be the first, I'll make this the first column. Really you can make it any column, but I'll make this the first column of that matrix P that I'm trying to create. Right, that'll diagonalize this matrix A. Alright, so that was when lambda was 4. Found an eigenvector, 1, 2. And I do the same thing when lambda is 5, right, the other eigenvalue. So again, I'm just going to do this. We're looking at a minus 5i. Right, a minus 5i, and then putting it in reduced echelon form, and just imagining you've got times x equals 0 and all that. So I'm taking matrix A, subtracting 5 down the main diagonal. And then I put this into reduced row echelon form, and we'd end up we're solving this system. Again, the first row just multiply by negative 2, add to the second row. The second row will be a bunch of zeros. And you have equals 0 on the other side. And the first row's already got a lead 1. And my second variable here, x2, would be free. It's not a pivot column. I'll just let it be t. Then from the first row, x1 would have to be equal to t. And just add t. So the eigenspace of A corresponding to lambda equals 5 is the span of the vector 1, 1. And there, this vector 1, 1, or any multiple of it, any scalar multiple of it. This vector 1, 1, I'll make this the second column of P. There, I have found my two independent eigenvectors. So then after I find all these n independent eigenvectors, we can create the matrix P that they say diagonalizes A. The matrix P that diagonalizes A. And it's simple. Matrix P that we're looking for is going to be a 2 by 2, right? Same size as A, where in one column was one of these eigenvectors. Right? I'll take the one from the eigenspace corresponding to 4, so 1, 2. And in the other column, another independent eigenvector. Right? 1, 1 would be independent of 1, 2. There. This is the matrix that diagonalizes matrix A. And let me show you. I will show you. Well, in order to see that, we need to find P inverse as well. All right. So first, what's the determinant of this? It's 1 minus 2, so negative 1. So the reciprocal of that's negative 1. Switch the diagonals and take the opposites of these. All right. So P inverse is the matrix with entries negative 1, positive 1, positive 2, negative 1. Okay. And let's see. Let me take P inverse times A times P to get another matrix that's similar to A. And what we're going to see is if I did this correctly, and the columns of P are independent eigenvectors of A, we're going to see that this produces a diagonal matrix. So again, write these out. P inverse times A times P. So I'm just going to go right to left here. P inverse, and then when I take A times P, I'm getting 6 minus 2, 6 minus 1, 2 plus 6, 2 plus 3. All right, and then multiply these two. Negative 4 plus 8. Negative 5 plus 5. 8 minus 8. 10 minus 5. And look at this. Diagonal. And also, look at the entries down the main diagonal. These are the eigenvalues. And it should be that way. Remember we said earlier, similar matrices have the same eigenvalues. And if you have a diagonal matrix, remember the eigenvalues are just the diagonal entries. So it should be this way, because A is similar to D. Yeah, so this is definitely a long process, but it will work whenever the matrix is diagonalizable, whenever the matrix has n independent eigenvectors. Okay. All right, so I'll definitely do another example of this. This will be a longer video, sure. But let's get back into the example. Now they have another one. All right. Not every matrix, I'll tell you right now, not every matrix is diagonalizable. All right, so let me just show you part C of that same example. So here's a matrix called C. That's another 2 by 2. And the same question. is C diagonalizable? Can you find a matrix P, right? Can you find a matrix P such that P inverse times this matrix C times P is equal to a diagonal matrix? D. Now again, the answer to this question depends on whether or not you can find two independent eigenvectors, right? Again, because this is a 2 by 2 matrix. We'll see a 3 by 3 matrix later. We'll have to find three independent eigenvectors. All right, so first I'll find the eigenvalues, right? Find the spectrum. So what's the determinant of C minus lambda I? And when's that equal to 0? So this is the determinant of, you got 3 minus lambda, 1 and 0. And when's this equal to 0? Well, I mean, I don't know why I even set this up, because this is upper triangular. So the eigenvalues are 3 and 3. Right? It's got an algebraic multiplicity. I'll just tell you right now, lambda equals 3. All right? And this is the only one. Right? This is the only eigenvalue. And to use a word from last section, the algebraic multiplicity is 2. Right? It shows up twice, so it would be a repeated eigenvalue. Alright, so I don't have two different eigenvalues like in the last example. Right? If the two eigenvalues are, if all the eigenvalues are different, then you're going to get an independent eigenvector for each one, and you'll definitely be able to diagonalize. So here I can't tell right away. I have to go further. Right? I have to check. So now I'm going to try to find the eigenvectors, right? So now we're going to look at, what is C minus, when lambda equals 3, what is C minus 3i? So that'd be 0, 0, 1, 0. And that's already in reduced row echelon form. So again, if I augment the zeros on the other side, when's this equal to 0? We're seeing that, x1 is free this time, right? Because the first column is not a pivot column. So I let x1 be t, and from the first row here we're seeing that x2 has to be 0. So the eigenspace of matrix C here, corresponding to lambda equals 3, is the span of the vector, x1 is 1 times t, and this is 0 times t, I guess you could say. So, every eigenvector is some multiple of 1, 0. Every eigenvector corresponding to lambda equals 3. And so the geometric, right, this has dimension 1, right? Right, this has a basis with only one vector. And remember, this was called the geometric multiplicity of lambda equals 3. And what are you noticing? Well, the algebraic multiplicity was 2, but I could only find one independent eigenvector, not 2. And since I can't find 2, and this is a 2 by 2 matrix, and I've exhausted all the eigenvalues, this matrix is not diagonalizable. C is not diagonalizable. Again, it's because it's a 2 by 2 matrix, and I can only find one independent eigenvector, this vector 1, 0. It's not 2. Right? And that's going to happen. Right? That's going to happen if for any eigenvalues, if the algebraic multiplicity and the geometric multiplicity are not equal. All right. So to rephrase that, the only way a matrix will be diagonalizable, right? The only way you're going to be able to do this is if every eigenvalue's algebraic multiplicity is the same as its geometric multiplicity. That way you'll be able to find n independent eigenvectors and then be able to form your matrix P and go from there. If any eigenvalue has unequal algebraic and geometric multiplicities, then the matrix cannot be diagonalized. You can't find a matrix P that does this. Okay. So I'll say it one more time. The only way a matrix is diagonalizable is if every eigenvalue's algebraic multiplicity is the same as its geometric multiplicity. And if you find if you find just one eigenvalue where the algebraic multiplicity is greater than the geometric multiplicity, then you can't diagonalize that matrix. Right. So again, you can read through the others. There's option, example B, example D there. All right. All right. So, I'll let you do these activities yourself. There's another 2x2. They're asking you again, is it diagonalizable or not? Same thing here. Now this one's an easy one. It's an upper triangular matrix, so all the eigenvalues are down the main diagonal. 1, -1, 0, 3, and 5 are the eigenvalues. And they're all different. Right? They all have an algebraic multiplicity of 1. And remember, no eigenvalue from last section, no eigenvalue can have it will have a geometric multiplicity of 0. That's not going to happen. It's always going to be at least 1. So if every eigenvalue has an algebraic multiplicity of 1, they're also going to have a geometric multiplicity of 1. So every eigenvalue's algebraic multiplicity will be equal to its geometric multiplicity. This one would be diagonalizable. All right. Okay. So now, I've already done an example of this. I've already shown you how to do this, how to diagonalize a matrix. Remember this, once you have found these n independent eigenvectors, the matrix P that was talked about, you just put those n independent eigenvectors as columns, and there's your matrix P. And then when you take P inverse times A times P, the diagonal matrix you get has the eigenvalues in that same order, right? In the same order that you put the columns in. It has the eigenvalues that they correspond to down the main diagonal. All right, and then again, I already talked about the procedure a little bit. Here are the steps. These are the same steps that I followed with that 2x2 matrix earlier. All right, so I'm going to do that again with a 2x2 matrix, and then maybe once more with a 3x3, and we'll call it a day. So here's the next 2x2 matrix. I'm telling you right now, right? This is a lower triangular matrix. Right? All the non-zero entries are on the diagonal or lower. So I can tell you the spectrum of A right now. Right? The set of all the eigenvalues, without having to set up the characteristic equation. They are 1 and -1. And they each have an algebraic multiplicity of 1. Right? So I'll make a note of that. Each of these, 1 and -1, have an algebraic multiplicity of 1. and so the geometric multiplicities are going to be 1. This is diagonalizable, right? If all the eigenvalues are different, right, if they all have an algebraic multiplicity of 1, your matrix will be diagonalizable. Okay. But now the eigenvectors, right? So now from each of these, I want to find an independent eigenvector to put as a column of the matrix P that I'm looking for. All right. So when lambda equals 1, all right, we're going to take a look at a minus 1i, a minus 1i. So that's this, subtract 1 down the main diagonal. And then put this in reduced row echelon form. So again, I would just multiply this one here by a sixth and move it to the top. So I'd have 1, negative 1/3, 0, 0. And again, you're imagining that we're going to have this times some vector equals the 0 vector like that. And the second component, x, I'll call it x2, is a free variable. It's not in a pivot column. And just to make sure I get rid of this fraction here, I'll say we'll replace x2 with 3 times t, right, where t is any real number. And then from the first row, we have x1 minus 1/3 of 3t, so minus t equals 0, so x1 has to be t. Right, we just add t to both sides. So the eigenvector I'm getting out of this, so I'll just say the first column of P is the vector 1, 3. Okay. Now you could use any multiple of this, right? Replace T with anything, as long as it's not the 0 vector, right? It has to be an eigenvector. But I'll just call that that'll be my first column of P, right? The eigenspace corresponding to lambda equals 1 would be, the span of the set with this vector. The set with this vector would be a basis for this, right? So that means that this, this guy here has this lambda equals 1 has a geometric multiplicity that's also 1, right? Because its eigenspace has a dimension of 1. So the algebraic, this is going to be the same for both of them. Now for lambda equals negative 1, I'm going to look at a minus negative 1i or a plus I. So that's just adding 1 down the main diagonal. So I'd have 2, 0, 6, 0. And again, put this into reduced row echelon form. Simple enough, just 1, 0, 0, 0, right? Because I can multiply the top row by negative 3, add it to the second row, get rid of those, make those zeros, and then multiply the top row by a half. And then again, we have the equals 0 on the other side. Now, this is simple enough, The second component, again, is a free variable, so I'll say x2 equals t, and then the first row is just simply x1 equals 0. So any vector in this eigenspace is going to be a multiple of 0, 1. So I'll call that, that'll be my second column of P. Be the vector 0, 1. Okay. All right, so let's put that together. All right, so the matrix P is this 2 by 2 matrix, where down the first column is this vector 1, 3 that corresponded to lambda equals 1. Second column is 0, 1 that corresponded to lambda equals negative 1. And then we're going to see that this matrix here diagonalizes matrix A. And how do we check this? Well, we need to see that, we'll have to see that A is similar to a diagonal matrix. So take P inverse times A times P and see that we get a diagonal matrix. Well, first, in order to find this, I need to know P inverse. All right. So, it's a 2 by 2, pretty easy. Determinants, 1. So P inverse is no problem. It's just 1. And switch these, opposites of these, so this here. There's P inverse. So let's see what we get. P inverse times A, which was 1, 0, 6, negative 1, times P. And if I did everything correctly, right, if I did everything correctly, what we should end up with is a diagonal matrix where down the main diagonal I'll have 1, then negative 1, right, because I put those vectors in that order. Right. So let's see. So again, I'll just do these two first. And you can do this on a calculator, do the matrix entries and multiplication. But I'm just by hand real quick. 1, 0, 6 minus 3 is 3, and then 0 minus 1 is negative 1. And then multiplying these, we get 1, 0, negative 3 plus 3, 0, and 0 plus negative 1, negative 1. Look at that. There's that diagonal matrix I was talking about. And again, look, like I said, look down the main diagonal. Those are the eigenvalues in the order I found the eigenvectors with. Right? The order that these come in correspond to the order that I put the columns of P. Wonderful. All right. Okay, so now again, you can read through the example, see it all written out. Now they did the characteristic equation, but again, it's easy to see that this was lower triangular, so you didn't need to do that to find the eigenvalues. All right, cool. All right, and then they have you kind of just go through step by step another 2 by 2 matrix here. First find the eigenvalues. Are they 5 and negative 1, true or false? And then, is this vector an eigenvector corresponding to lambda equals 5? Is this vector an eigenvector corresponding to lambda equals 2? And if these are, then would this matrix P diagonalize A into this diagonal matrix? So just kind of leave that to you. Oh, looks like I have an activity that failed to load here. So I'm going to see if that comes back to me in a second. Alright, so I refresh the page, and here we go. They basically are having you verify that this matrix is diagonalizable by finding, 2 independent eigenvectors. Actually, they're telling you what the eigenvectors are. Okay, so remember, you just set it up so that 2, 1's the first column of P. They have A equals P d P inverse, right, the other way. So P times the diagonal times P inverse should give me A. I was doing that P inverse times A times P should give me the diagonal. Same thing, just in reverse. So I put 2, 1 here, 1, 1 here. Remember, the order that the entries come in down the diagonal will be the order of the eigenvalues with their corresponding eigenvectors. So if I put 2, 1 here, 1, 1 here, this would be the inverse of P here, and then this would be 3 and 2 down the diagonal. And you could multiply these matrices and see that you'd get matrix A again. All right, let me get to see if there's any 3 by 3 examples. Here's another 2 by 2. Another 2 by 2. Another 2 by 2. Okay, so maybe we'll get to a 3 by 3 eventually. All right. So now on to some properties of diagonalizable matrices. And all of these properties, except for number 4, the first 3 properties are just because that these matrices are similar. Remember the properties of similar matrices that were stated, earlier in this section, earlier in this video. I know it's been over an hour, but similar matrices have the same determinant. Similar matrices are either both invertible or both non-invertible, and that's because they have the same determinant. Similar matrices have the same rank, the same nullity, the same eigenvalues, right? So these first three properties they're mentioning here are the same, are simply because A and this diagonal matrix are similar. And then this was also mentioned before, that if you raise A to a power, you can calculate A to a power instead of multiplying A by A by A by A by A k times. You only need to find the product of three matrices. That P, the D to the K, which again, a diagonal to a power is easy. Just raise all the diagonal entries to that power, and then times P inverse. So I'll get to an example where we actually raise to a power here in a second. And they run through proof and all that if you want to read that. Great. All right. So you know what? I actually just want to do the diagonalization of this myself. And you see at the end they want us to find A to the 7th. All right. Okay. All right. So I'm going to go through the whole process again. All right. But skipping some steps. I'll pause the video and have some things written out and come back. And then when I do the matrix multiplication, I'll do it on a calculator. Right. Same thing for finding inverses and stuff. So first I want to determine, the spectrum of A. So setting up that characteristic equation, right, as usual. When is the determinant of A minus lambda I equal to 0? So that's this. You got 1 minus lambda, 1 minus lambda, 1 minus lambda down the diagonal, and 2's everywhere else. Alright, and then this is a 3 by 3 determinant. So I'm just going to do some cofactor expansion here. So starting the first row, first column, do 1 minus lambda times the determinant of, the lower right, what's left over, the minor. Then minus 2, right, because again, this is in an odd position, so the cofactor will be the opposite of the minor. That's why I'm going minus 2 times the minor. Oops, should be 1 minus lambda. All right, there we go. It's a 1. That's a big, thick 1. And then finally plus 2 times the minor 2, 1 minus lambda, 2 and 2. Alright, so I'm going to skip ahead. I'll come back when I'm done writing this all out, taking these determinants, these determinants, these determinants, and factoring this all completely. So I'll be right back, just pausing it for a brief second. Okay, so a lot of writing just popped up on your screen, I'm sure, right? Went through the determinant, did all this, did a lot of factoring. If you're not following the algebra, take it nice and slow. But eventually you should have factor this polynomial to -1 times lambda plus 1 squared times lambda minus 5. And when's that equal to 0? Well, when lambda equals -1, right, so -1 is in the spectrum of A, and when lambda equals 5, right? And their algebraic multiplicities. I'll just say AM for algebraic multiplicity. The algebraic multiplicity of -1 is 2. And the algebraic multiplicity of 5 is 1. Alright, so they don't all have, multiplicities of 1. So I can't tell if it's diagonalizable yet. I would like to find, it's a 3 by 3, so I would like to find 3 independent eigenvectors. So what I'm hoping for are two eigenvectors in the independent eigenvectors in the eigenspace corresponding to lambda equals -1, and I'm hoping for one from lambda equals 5, right? Because I want again the geometric multiplicities to be equal to the algebraic. All right, so for lambda equals -1, so we're going to look at a plus I, right? A minus -1 times I. So that's just adding 1 down the main diagonal here, and this is just, just a bunch of 2's everywhere. So this is real easy to put into a reduced echelon form. I don't need to do a calculator with this one, because I can just get rid of these 2 rows here by taking the opposite of the first row and adding them, and then I would multiply the top row by a half to get 1, 1, 1, and you got 2 rows of zeros, and then you got the equal 0 thing over here. So my free variables are, the second component, I'll call that S, and the third component, I'll call that T, where S and T are any real numbers. And then from the first row, you see that x1 would have to be -s minus t, right? Subtracting x2 and subtracting x3. So hopefully you can see that the eigenspace of A corresponding to lambda equals -1 is the span of, and then 2 vectors. I do have a geometric multiplicity of 2. The geometric multiplicity is equal to the algebraic. That's great. I can find 2 independent eigenvectors from this. Coefficients of S down the components are -1, 1, 0. And the coefficients of T, -1, 0, 1. Alright. So, I'll make these the first 2 columns of my matrix P. Right? Two columns of P. And again, the geometric multiplicity, so the geometric multiplicity, GM, is equal to 2 as well, right? This has dimension 2. If it wasn't 2, if it were 1, then I'd stop and say, oh, this matrix can't be diagonalized. But it can so far, right? Well, now I know it definitely can, because I'm getting 2 from here. And if your algebraic multiplicity is 1, the geometric multiplicity is also going to be 1. So I'm going to get 3 independent eigenvectors. Alright, so now when lambda equals 5, I'm looking at A minus 5i. So again, this is taking matrix A and subtracting 5 down the main diagonal. So it'd be -4, -4, -4, and then 2 everywhere else. I'll put this into reduced row echelon form. Now this one's a little trickier. So I'm just going to pop that up on a calculator. Alright, so again, something just popped up on your screen, and I put this 3x3 matrix on my calculator, ran it through the function reduced row echelon form, got this one here. x1 and x2 are basic, right? So there's only one free variable, and there should be, right? The algebraic multiplicity was 1, so the geometric multiplicity should be 1. So again, I'll call this t, and then from the first line we're getting x1 must be t as well, and same thing from the second line. x2 must also be t. So the eigenspace of A corresponding to lambda equals 5 is the span of the set with the vector 1, 1, 1. And I'll make this the third column. There's another column of P, this other independent eigenvector. Okay, so this matrix P I want to make, and I think they put it in a different order. But the order that you put these vectors, all that's going to do is change the order that the diagonal matrix comes in, that the diagonal entries, the order that the eigenvalues come in. So I'm making this 3x3 here, where my first 2 columns are these vectors, when that corresponded to the eigenvalue of -1. So -1, 1, 0, -1, 0, 1. And the third column, I'll make this vector that corresponds to lambda equals 5. All right, and since I found 3 independent eigenvectors, this matrix should diagonalize matrix A. And what should happen? All right, what should happen? Since I did everything correctly, I feel, is that P inverse times A times P should be equal to a diagonal matrix. And again, this diagonal matrix, I know what it's going to be, and I'll show you on the calculator. The entries down the diagonal will be the eigenvalues that correspond to these columns of P, which the first 2 were corresponding to -1, and the last column I had corresponded to 5. All right, and then every other entry will be a 0. All right. So let me show you this. Let me verify this on my calculator. Okay, so what I've done now is I've entered on my calculator matrix A. If I go to the matrix menu, this is matrix A on my calculator, the 3x3, and the matrix P on my calculator is matrix B. All right, so matrix B is P. And the matrix D is actually matrix D, and C is nothing. Don't worry about C. That's from an earlier problem I was doing that I couldn't erase. All right. So A is A, B is P, and D is D. So let me show you. Let me take B inverse times A times B, and you'll get this diagonal matrix. So B inverse times matrix A times matrix B, and you see, well, okay, calculators do rounding and stuff. Remember, this e to the -13 means move the decimal place to the left 13 places. That's a 0. That's a 0. So it is a diagonal matrix with down the main diagonal -1, -1, 5. So it is D here. All right. So now let's do what they want. All right, let's do what they want. They asked us to, well, I mean, part of this activity is, say I asked you to find a to the 7th power. Now you could, right, you could multiply, a by a by a by a by a, 7 times. And by hand that would take a while. Yeah, I know I can do this on the calculator. If I go, here's the matrix, matrix A raised to the 7th power. I get a lot of big numbers there, right? I have to scroll through. So yes, I get that. But what if I wanted a to the 100th power, the 1000th power? Your calculator might not be able to enter that stuff. All right, but you can write it out by hand. All right, so let me show you how I would find a to the 7th first. So remember, if this is the case, if P inverse times A times P is this diagonal matrix, that means that A is, P on the left to get rid of the P inverse, then P inverse on the right. We're getting this. And A to the 7th then would be, and again, you would multiply this by itself 7 times, and a lot of P's and P inverses would cancel, and be left with the P on the left, then times D to the 7th, and then you'd be left with the P inverse on the right. Okay. So you only need to multiply, 3 matrices instead of 7. So I'd have P, right? P is this guy here again. Right. I'm not going to write it again. Right, we'd have P. Now again, D to the 7th would be very simple. D to the 7th would just raise the entries to the 7th power. Now -1 to the 7th is -1. -1 to the 7th is -1, and then you have 5 to the 7th, whatever that is. and zeros everywhere else. It's very easy to raise diagonal matrices to powers. Alright, and then you have P inverse. Alright, so again, I'll do this on the calculator and show you that these are the same. Alright, so P was matrix B on my calculator, right? So I'm going to take matrix B times, and then, matrix D on my calculator was the D to the, the diagonal, and raise that to the 7th, times, and then, P inverse, so B inverse on my calculator. And I'm getting, see, the exact same matrix that I got before when I raised just A to the 7th. Alright, the only reason that this is helpful though is because if you were doing this by hand, right, it would take a lot less time to do, multiplication of 3 matrices by hand than it would be to do 7 matrices. Alright. And it's also easier to write out, A to the 100th, A to the 1000th, A to any power by hand this way than even it would be on a calculator. So another useful application, a nice useful application of diagonalization. Alright, now here again they put them in the other order so that, 5 is first and then you got two negative ones. See how they put the 1, 1, 1 first? I put it in the third column, whatever. Where are the eigenvalues? What would be the determinant of A? Remember, this was mentioned, I think, back in section 8.1. Remember, the determinant of a matrix is the product of the eigenvalues. Also, remember that two similar matrices have the same determinant. So the determinant of A should be the same as the determinant of D because they're similar. And the determinant of a diagonal matrix is just the product of the diagonal entries. So positive 5, right? What would be the rank of A? It should be the same as the rank of D in every single, there are 3 independent column vectors in D, so their ranks are both 3. And if their ranks are both 3, their nullities are both 0. Remember, rank plus nullity equals the number of columns. And finally, A to the 7th would be this times this times this. Here I'm putting 5 to the 7th power. Alright, 5 to the 7th power, whatever that is, would go here. Alright, and then you have, alright, so that was a long one, an hour and a half now. But there was a lot of stuff here, right? The concept of when are two matrices considered similar, some properties, is a matrix diagonalizable or not? Does it have, n independent eigenvectors that you can then use as columns of that matrix P and so on? And then raising the powers, right? You had a lot of stuff going on here. And then you have your additional exercises, which, some of these are in the assignment, some are not. I would still recommend looking at all of them, all right, just for extra practice, extra exposure, maybe get better at the material. And, you got the solutions to look at if you need to. All right, and please, try to work things out before you look at the solutions, right? Don't just copy solutions down, because you're not going to learn anything that way. All right, and I hope this is a nice guide for you for this section. Let me know if you have any questions, right? Send me a message if you have any questions, and I'll get back to you as soon as I can. And thank you very much for watching.